line section is generation of rotationality. This is the second time we have discussed Bernoulli's equation under different circumstances. Such reinforcement is useful since this is probably the most widely used equation in fluid mechanics. It requires frictionless flow with no shaft work or heat transfer between section 1 and 2, for example. The flow may or may not be irrotational, the latter being a easier condition allowing an universal Bernoulli constant. A fluid flow that is initially irrotational may become rotational if the fluid flow that is initially irrotational may become rotational if one, there are significant viscous forces induced by jets viscous forces induced by jets, wicks, or solid boundaries. Jets, wicks, or solid boundaries. In this case, Bernoulli equation will not be valid in such viscous region. So Bernoulli equation is not valid. 2. There are entropy gradients caused by curved shockwaves. Gradients caused by curved shockwaves. And 3. There are density gradients caused by stratification. Rather than by pressure gradients. There are significant non-inertial effects. And 4 at last. There are significant non-inertial effects such as Earth's rotation. rotation. In the case 2, 4, Bernoulli's equation still holds along a streamline if friction is negligible. We shall not study case 3 and 4 in this book. Case 2 will be treated briefly in the next chapter on gas dynamics. Primarily, we are concerned with case 1 where rotation is induced by viscous stresses. The case 1. This occurs near solid force surface where no slip condition creates a boundary layer through which the stream velocity drops to zero, and in jets and wakes where a stream of different velocities meet in a region of high shear. Internal flows such as pipes and ducts are mostly viscous, and the wall layers grow to meeting the core of the ducts. Also, Bernoulli's equation does not hold in such flows unless it is modified for viscous losses. In the case of the validity of the Bernoulli equation, consider this picture for a description is on each part. The first part is the viscous region where Bernoulli's equation fails, and the part B is the curved shaft wake introduced rotationality viscous region where Bernoulli is invalid. External flows such as a body immersed in a stream are partly viscous and partly inviscid, the two regions being patched together at the edge of the shear layer or boundary layer, as shown in this picture. Two example figures are here, shows a low-speed subsonic flow past a body. The approach stream is irrotational, that is, the curl of the constant is zero, but viscous stress creates a rotational shear layer beside and downstream of the body as shown on the picture. Generally speaking, the shear layer is laminar or smooth near the front of the body and turbulent of the or disorderly toward the near. The separated or deadwater region usually occurs near the trailing edge, followed by an unsteady turbulent wake extending far downstream. Some sort of laminar or turbulent viscous theory must be applied to these viscous regions. They are then patched onto the outer flow, which is frictionless and irrotational. If the stream Mach number is less than about Mach number, if the stream Mach number is less than 310 that we obtained before in previous video in this chapter, we can combine the equation of rotationality, which was equals to potential function equals to 0, and we can write equals to 0. This is the Laplace equation in 3 dimensions, there being on restraint on the number of coordinates in potential flow. Laplace equation three-dimensional. There being no restraint on the number of coordinates in potential flow, the grid DL available in Chapter 8 will be concerned with the solving various equations. The next section in this chapter is some illustrative incompressible viscous flow, which are available in next video.